All right. So today we are taking a look at a section called superposition approach. And we have actually looked at the principle of superposition before, like last week. And we didn't talk a lot about it, except this idea that the superposition principle really allows us to use the idea of linear combinations in order to represent an actual solution. Okay. Now, what do we know? Last week, we focused really heavily on the homogeneous second order differential equations. And we looked at sort of two different flavors of those. We looked at the ones with constant coefficients, and we looked at the ones with non-constant coefficients. And so what we're going to do today is we're going to take a look at non-homogeneous second order differential equations. Right. And we're going to focus the start of this week on ones that have constant coefficients. Okay. And so with that, here is a sort of part 2 to the diagram that we've seen some version of. Okay. And so before, this was for homogeneous second order differential equations. And where we're going this week is specifically around the non-homogeneous ones. They break up into two similar categories, one that has constant coefficients, one that has non-constant coefficients. And today we're going to take a look at what happens when we have these undetermined coefficients. And it turns out we'll use this principle of superposition. And so this we could say is 4.4. All right. If you are curious about this annihilator method, that is in section 4.5. We will not cover this section. It's just not used as much. So we will not cover that section, but it is another method if you want to take a look at that and sort of add that to your toolkit. But these two methods really only work for a very specific case. And so it's important that we consider more general cases. And in order to do that, we're going to take a look at something called variation of parameters, which will be in the 4.6 video. And then the second branch here deals with the non-constant coefficients. So when we have like functions of x as the coefficients, and the method we will learn here is called the Cauchy-Euler method, right? And they deal with the Cauchy-Euler types of equations. And so a general theme that we're going to continue in this chapter is, what kind of equation is this? How do I know? And what method is going to fit that equation? All right. So if that's how you've been studying for this class, that is a really good way to make sure that you know, come in exam, how do I know which method to use where? Okay. So we're going to start off with a little bit of some theory. Okay. And so one thing that we know is we're looking at second order differential equations. So like a y double prime. And if we think about a second order linear differential equation, we might remember from the very first week that, you know, maybe we had a coefficient here, but we divided through by it and got these new functions, p of x and q of x. And up until this moment in time, we've always had it equal to 0. And that's what we said was making it homogeneous. Now, we're not going to have an equal 0. In fact, we're going to have it equal to some function of x, and we'll call that function g of x. Okay. Now, the way this is going to work is this. When we think about solving these, okay, our first step will be to look at something we call associated homogeneous differential equation, meaning what if we had just the left-hand side and it was equal to 0? All right, so all those skills that we learned last week are going to come into play to help us figure out the first part of a non-homogeneous differential equation, okay? So we're gonna look at that homogeneous differential equation and we're gonna see what solutions it has, all right? Should have solutions that look something like this. C1y1 plus C2y2. So that principle of superposition, all right? But what we're gonna call this now is we're gonna call this y sub c, all right? Y sub c. And I'll tell you what that means. This y sub c stands for the complementary solution. So the C stands for complementary, okay? So you're looking for the complementary solution. That's the first step. So we look at the side that is the differential equation part. We look at this. We find some solutions knowing how we did them last week. We use those same methods. And then for the second part, we come back and we take a look at the part that makes it non-homogeneous. And so we're gonna use g of x to find something we call y sub p, all right? And the y sub p is a solution just like the y sub c, except this one we call a particular solution, all right? So we're gonna have a complementary solution that is basically like the homogeneous part solution. Then we have to find the other part of the solution, the particular solution that goes with the non-homogeneous part. Together, they will make the overall solution. So our ending piece for these non-homogeneous questions should be y sub c plus y sub p. All right, so at the end, our solutions are going to look a little bit longer than they did last week because we have to compensate for the non-homogeneous part. All right. And so that's where we're headed. All right, that's where we're headed. Some of these questions, we're just going to practice finding the particular solution. Some of them will practice finding the particular and the complementary solution. Okay, so it would be really important to read the question carefully so you know what you're trying to find. All right. All right, so we're going to come back to these in a little bit because I think that it's important to have them here to access, but we'll make sense of them in the context of a problem. Okay, so we're going to come back to this page. These two tables, this first one is actually from your textbook. Oh no, this one is from Paul's online notes. The second one is from your textbook. Okay, so different tables out there sort of have varying amounts of information. We probably, between these two tables, will have all the ones for our particular solutions that we need, okay? But one key word to focus in on here is the word guess, all right? So if this has been making you uncomfortable, it is sort of a part of the process of differential equations where we say, here's what function we have. And so here's a guess as to what the solution might look like. All right. And in the beginning, it's really hard to say, well, here's my non-homogeneous part. So I'm going to guess this. Like it's hard to just kind of guess out of thin air. So that's why I gave us the table so we could kind of use this to guide our guessing. Okay. But all of these are for the particular solutions. Okay. So the little y sub p, that p is for the particular solution. We're going to use our methods from last week to look at the complementary solutions. Okay. So let's take a look at an example. This first example will really focus on looking at the table and trying to guess the form. Okay, so now one of the sad things about being remote like this is I can't share two screens at the same time. Okay, so I see that there are some people on the notes in the Google Doc, but if you have that there, maybe we can use that to sort of match with the examples that we have here. Okay, and so I'm wondering if we can take a look at this first example here. And what this means is we're saying we have some g of x, like the other side of a differential equation, the part that makes it non-homogeneous. And let's say it looked something like this. And this would be like a really complicated one to ask you to do, okay? But what we're going to do is you go back to the table and we're going to look for what happens if we have like an e to a something. And then we're going to look at what happens when we have like a sign of something. And we're going to use this to quote unquote guess our solution form. Okay. So let's go back up. We're going to take a look at first, let's find the e to the 7x, and then let's find the sine 10x. Okay. So it doesn't really matter which table you use. I think that they're both fairly similar, but we might notice that this first line here, when I have e to the beta t, a good guess for that is e to the beta t. Okay. Now, the second term we had was sine of 2x, so maybe that looks something kind of like this one. And so we might want to choose this third one right here. Okay, so using the top table, the one from Paul's online notes, it looks like it's going to be this one and this one. But you might be asking yourself, like, what do we do when the functions are multiplied together? And so that's where I think this table from your textbook is a little bit handier, because this e to the 3x sine 4x is actually really close to what we had. We just had like different numbers, right? We had e to the 7x sine of 10x. And so it turns out that our guess for our solution form is going to be something like this. A to the 7x in our case, cosine 10x, plus b, e to the 7x sine of 10x. Okay. Now I'm wondering if you can help me out here. This was one choice, this was a second choice, and then this is how your textbook sort of combine them. How do you think they got from the two pieces in the first table to the single piece in the second table?
Just distributive property?
Yeah, distributive property. So it turns out that when we have two functions that are multiplied together like this, if we only had a table that showed like individual ones, if we're multiplying, we're going to grab both solution forms and we're just going to multiply them together. And when we multiply them together, we'll get the form for the product of those two functions. Okay. And so if we go back down here, maybe I can grab this. This is the form that we are looking to match, all right? And so if we think about what our y sub p might be, we would leave these as like, we would leave the a and b as they are. Okay, so we would say a e to the 7x cosine 10x plus b e to the 7x sine of 10x. Okay, so we're basically using the same structure that they had in the example, but we're just changing the numbers to match what we have. Okay. Now, one important piece to notice here is this 16, we actually don't really worry about that. And the reason we don't worry about that is the same reason that we have sort of not been worrying about our individual constant values as we go along, because that actually gets taken care of in terms of the a and the b. Okay. Now, some people like to distribute it out. Other people prefer not to distribute it out. And so they might write it like this. And either way is fine. Okay, so either way, if I say guess the form of the particular solution, you can either find the product already distributed on the table, or you can write it as the product of two separate ones that you find on the table. All right. So knowing that, we have 4 more here. Okay, I'm wondering if we can take a look at g of x equals x cosine x, all right? So use the tables on the previous page to guess a form for example 2. And once you think you have that, go ahead and type that into the chat. Let's see what we get. Anybody think they find the form that comes when we see just an x? All right, let's see. We have a guess for AX. So I would say that X is probably most similar to like a 5X plus 7 situation from the bottom table. Right? And it doesn't look like we really have one here, except that they describe in general the nth degree polynomial. So if I have X, what degree is that? Yeah, that's a first degree. And so for first degree, we actually need the AX plus B. All right, so we do need the AX plus B because we're just sort of chopping off the last 2 values here. If we had a constant, then we would only need the A sub 0. But since we have a linear or a first degree, we need like an AX plus B situation. Okay, so we're actually going to grab the whole thing, AX plus B, even though that constant is 0 in the X term. Okay. So if I go down here, I can write this as AX plus B. And guesses to the cosine. How am I going to generalize the cosine? Good. So C cosine X plus D sine X. Good. And because there's the coefficient up here was 10, that's why I had the 10 here, but since the coefficient is 1, I just still have a coefficient of 1 here. All right. So that could be one way that you look it up. You say, I find both of them, and then I know that my particular solution is just going to be the product of the general form from the linear one with the general form of the cosine. Okay. That is one way that you could write that answer. You could distribute if you want, but I think this would require like a FOIL-y sort of situation, which might make it longer and actually harder to see the pattern than anything else. Okay. All right. Now, the first two examples we did were all with multiplication. Okay. But if we take a look at these last three, we start to see some addition and subtraction. And it turns out that addition and subtraction just mean that we can take each one, find its general form. So find the general form for the 3x squared. Find the general form for this middle term, and then find the general form for the last one. And then we can go ahead and subtract the first two and add the third. Okay, so addition and subtraction are always much nicer than the multiplication, right? We don't have to worry about special rules quite so much. But if x, the general form of that solution is ax plus b, what do you think the general form of 3x squared solution is going to be? Good, good, good. Yeah, it's a quadratic. And so we're going to go ahead and make sure we have our ax squared plus bx plus c. All right, so this will correspond to that first term. All right, and then what do we think is going to be a general form for the yellow piece? Well, that's the sine. So it's very similar to that first problem. So we're going to have minus. And then one thing that I noticed who was it, David already did, is using different letters for all of these. So if we have C, then the next one will be D. So we can say D cosine of 2x plus E sine of 2x. And that would be a guess for the general form of the second part of the solution, plus, all right, we've got x e to the 6x. So are you saying like, could we just start to use like A, B, and C again? Yeah, we cannot. Okay, we cannot. So because they're coefficients for different terms, we want to make sure that we have them as different letters. Now, if you wanted to use the same letter, it would be okay to do like C sub 1, x squared, plus C sub 2, x, plus C sub 3, plus C sub 4, sine of 2x, or something like that. So if you want to use subscripts instead of different letters, you're welcome to do that.
Okay, thank you.
You're welcome. Okay. All right. So for this last one, x e to the 6x, let's go back up to our table. Let's see if we have any that are kind of like that. I bet we could grab this one right here, right? Because even though this is 9x minus 2, 9x is a minus 2 is a linear function, and so is x. And so we could say ax plus b times e to the whatever power we have. Okay. And so if we go back down here, we can say AX, oh, already used the A. So what letter are we on now? FX plus G e to the 6x. This would be the part that comes from the third term. Okay. So if we have pluses or minuses, that's how we handle those. Okay. So I will leave these two for you to practice, all right, writing those out. I will, when I post the notes for this, I'll go ahead and fill those in. But unless there are any questions, like you would definitely like to see another example, I feel like maybe we can move on. How are we feeling? We like to see another example. Are we okay? All right, so now let's figure out why we need to guess these solutions, right? So this is sort of like this is going to be the second piece of what we do, but let's take a look at a question and sort of this one will be the longest question that we do today, okay? In the sense that it will have all of the steps, like this is a very complete problem. So we are going to be determining a particular solution. That means we're looking for y sub p. Okay, so we're looking for the particular solution, and then we are going to be solving the initial value problem with these given initial conditions. Okay. All right, so let's go ahead and start from the top. So even though this says to find a particular solution, our first step is going to be to find the complementary solution. And the reason being, at the end, I see that I want to solve the initial value problem. And so I'm going to need my y sub c and my y sub p. All right. The other reason why I want to start with this is I think it's a good review of what we did last week. Okay, so to find y sub c, we are going to solve the associated homogeneous differential equation. That is, we're going to take y double prime minus 4y prime minus 12y, and we're going to solve. We're going to solve like it equaled 0. Okay. So last week's discussion, I said, hey, I want you to know what 3 different cases are, right? I want you to know what the 3 different cases are. And so if I see these, I see the constant coefficient. I see that I can write the characteristic equation that goes with it, all right? And we can use M or we can use the letter R. It's really up to you. But once we factor it, we'll be able to determine which of those 3 cases we will need. And so we notice here that M equals 2, negative 2, and positive 6, right? So you see your homogeneous constant coefficients, you think characteristic equation, and you think factor, and let's see what kind of roots we get. Now we have 2 real and distinct roots. What is the general form of that solution? Right, and that might be something you look back at your 4.3 notes at. But what is the general form of that solution? Good, good. So we have C1 e to the m1x plus C2 e to the m2x, or R2. Okay, now one thing I notice here is that equation you have is great if we had repeated roots, but we actually have distinct roots, and so we want to choose a different form. Okay, so we don't have an x in this one, but rather we're going to have both roots and just e to some power. All right, so we're going to plug this in. All we need to do is plug in our roots. So we get y sub c equals c1 e to the negative 2x plus c2 e to the 6x. All right. Now, I'm not going to put like a final, box around this or anything, but I do like to keep track of my work. And so I know at some point I'm going to come back and need this because I will have like y equals y sub c plus y sub p. Okay. So that's a little review from last week, solving that associated homogeneous differential equation. But now let's practice what we just learned in terms of reading the table, which is to find your particular solution, y sub p. So to find y sub p, we are going to guess a solution form from the table. Okay, so you're going to guess a solution form from the table. This is based on your g of x, right? This is based on whatever is making it not homogeneous. And so if we look here, we have 3e to the 5x. And so what is a good guess for a general form for that right-hand side? Right, so go back to that table. What's a good guess if we have e to the 5x as our non-homogeneous g of x? Yeah, we could say that is a e to the 5x. All right, so this one's not so complicated. We're not multiplying anything. We're not even adding anything. It's literally just one right from the table. Okay. Now, what we're going to do here is we're going to find our first derivative and our second derivative. We're going to plug things in to that left-hand side. Okay, so let's go ahead and find our first derivative. All right, so first derivative, I'm going to need chain rule. So it's 5a e to the 5x. And yp double prime is going to be 25a e to the 5x. All right, so we find those derivatives. Now we're going to plug those in to the differential equation. Okay, so what are we going to say? We're going to say that we have y double prime minus 4y prime minus 12y. Okay, so I just took the solutions and the derivatives, plugged them into my equation, and I want to make sure this equals my g of x, which in this case is 3e to the 5x. Okay. All right, let's do some computations. 25 AE to the 5x minus 20 AE to the 5x minus 12 AE to the 5x equals 3E to the 5x. All right, let's see. 25 minus 20 is 5. 5 minus 12 is negative 7. AE to the 5x equals 3E to the 5x. If I divide both sides by e to the 5x, those are going to reduce. And then when I solve for a, I will get negative 3 over 7. Okay, so in a similar fashion to what we've been doing since day one, we find some derivatives. We substitute them into our differential equation to see what makes it equal the other side. And we're able to find a constant that goes with it. So here's what this means. This means that y sub p, our particular solution, is going to be not ae to the 5x, but rather negative 3/7 e to the 5x. Okay. So we started by solving the associated homogeneous differential equation. We found our complementary solution. Then we went on to find the particular solution. This was all based on the guess that we made based on the form of our g of x. All right, we took some derivatives, we substituted them in, we used algebra to determine the value of those constants. In this case, there was only one, but you may find more than one, depending on what the form looks like. All right, now to solve the initial value problem, here's what we're going to do. We're going to write the entire solution first. That is, y is going to be y sub c plus y sub p. And we're going to write it out as like a whole long thing. C sub 1 e to the negative 2x plus c sub 2 e to the 6x minus 3/7 e to the 5x. And so we have our y sub c, which we said is this. And then we have our y sub p. This would be my y sub p. And so I have that on the end. All right, so we have another sort of linear combination. We have y equals y sub c plus y sub p. It's so important that you write out this entire solution because we're trying to find values now for C1 and C2. But in order to make sure we've plugged in everything in the right place, we need to make sure that the y sub p is there. Okay. And so these numbers, what do they give us? They tell us that y of 0 is 18 over 7 and y prime of 0 is negative 1/7. So I'm going to go ahead and substitute in the first initial condition. So y of 0, we said is 18/7, which is everywhere I see an x, I'm going to put a 0. So C1 plus C2 minus 3/7. All right. Are we okay where all the other terms went to when I wrote this? right? All we're doing is plugging in a 0 everywhere we see an x. And so e to the 0 is just going to be 1. So a lot of these terms go to 1 and we don't see them anymore. All right, before I write my or apply my second set of initial conditions, I'm gonna have to take the derivative, okay? Because the second one is like a y prime one. So we have to find y prime before we can plug in those second initial conditions. And so y prime here gives us negative 2c1 e to the negative 2x plus 6c2 e to the 6x minus 15 over 7 e to the 5x. And this initial condition says that y prime of 0 equals negative 1/7. So everywhere I see an x, I'm going to go ahead and plug a 0 in, and I'll get negative 2c1 plus 6c2 minus 15/7. I can take this equation and this equation, and I can go ahead and put them into a matrix if I wanted to. I could use substitution or elimination, all right? So any one of those methods would work. And at the end, we should find that C sub 1 equals 2 and C sub 2 equals 1, right? Now, these coefficients are integer values, but more often than not, we're going to find that they're actually some sort of fraction value, okay? I would say leave them as fractions, because if we start rounding with these constants, we're going to end up with other constants that might then be wrong, okay? So I've seen a few people do this on exams and on homeworks. It's probably not the population who's sitting with me right now watching this. However, in case this was you, if all you do is say, I found my C1, C2, and you put a box around that and you don't write anything else, then you're not going to get full credit for this. So you want to make sure that you go back to your Y, you plug in the C1, you plug in the C2, and then you can put a box around that for your final answer. So this would be your final answer for that initial value problem. All right, so there it is all on one screen. But the idea, this sort of process that we're doing, we're going to solve for y sub c, find that associated homogeneous differential equation solution. We're going to find y sub p, and then we're going to put it all together before we apply our initial condition. Okay. Now for some of the other questions, right, we'll be focusing more on finding the first two pieces, like finding y sub c, finding y sub p, putting them together, but we won't necessarily have the initial condition part. Okay, so at that point, it would be sufficient to leave your answer as sort of this long string of y sub c plus y sub p. All right. Before we move on, are there any questions that are coming up for folks right now? Okay. All right, so let's try another one. Okay. So in this case, it says, determine a particular solution to the non-homogeneous second order differential equation. Y double prime plus 4y prime minus 2y equals 2x squared minus 3x plus 6. Then determine the general solution. So the first part is asking us to find the y sub p, but the second part, determine the general solution. This is saying, I want the whole y. I want the complementary part and the particular part, all right? Now, I don't know why. I like to start by finding the y sub c. I think maybe there's a part of me that's worried that I'm going to forget to do it. And so then I'll only have a particular solution. That's maybe one reason why I do the y sub c first. I think the other part of me that says I want to find the y sub c first is because it goes back to something that we learned last week, and it gives me a chance to review that material. But whatever order you prefer here is fine. But let's, because I'm doing the writing right now, let's find our y sub c first. Okay, but if you like change the order in which you do it on a homework, like no big deal. Okay, so finding our y sub c. What does that mean? That means I have to look at the left-hand side, my differential equation side, pretend like it was homogeneous, and use that to find my y sub c. Okay, so if I pretend that this is homogeneous, I will see that I get m squared plus 4m minus 2 equals 0. Ooh, I don't think that factors. In fact, I think we're going to end up with some imaginary business. Let's see, -4 plus or minus 4 squared is 16 minus, oh, no, not imaginary. 4 times a times c is plus 8 all over 2a, which is 2 times 1. And I think with a lot of these, they tend to reduce so that there's not any fractions anymore. And remember, I'm looking for that lambda and mu. So it would be important to simplify this more than what I have right now. Okay, not in this case because it's not imaginary, so we don't have the lambdas and mu's, but as sort of like good practice, I think if we simplify this and we get in that habit when we are looking for lambda and mu and we have the imaginary, it'll be easier to do that step. Okay. So we have -4, let's see, 16 plus 8 is 24, which is 2 root 6. And we get -2 plus or minus root 6. Right? So we have real solutions here, right? Even though there's a radical, this is a real solution because there's no negative under that square root. And they're different from each other because -2 plus square root of 6 is different from -2 minus square root of 6. And so we can write our y sub c as c1. And we're going to have e to the -2 plus root 6 x. All right, that's going to be the first term plus c2 e to the -2 plus root 6, or sorry, minus root 6 x. All right. And maybe let me box this off in the pink because this is going to be part of a larger solution. Okay. So the skills from last week, we already see that they're part of a bigger problem, right? Like we're going to use those methods in the context of a bigger problem. And so if last week you weren't really sure on like memorizing those 3 forms, it's probably going to be helpful, at least for the next few weeks, to have those memorized or have them like on an index card right next to your computer or something like that. Okay. All right, let's find the y sub p that goes with it. And so this is where we're going to take a look at the right-hand side, the g of x, and we're going to guess a solution for it. All right. So y sub p, a good guess for this, well, I see a quadratic, right? 2x squared minus 3x plus 6 is quadratic. So a good guess for my y sub p would be ax squared plus bx plus c. All right, let's find that first derivative. What will that give us? 2ax plus b. Let's find that second derivative, 2a. All right, the quadratic ones are kind of nice because it's just power rule. And so we can move through those maybe a little bit more easily than things with chain rule. But now we're going to take these y sub p, y prime, y double prime, we're going to plug them into that left-hand side. And we want to see what values of a, b, and c make it equal to the right-hand side. B is a constant, so when I take the derivative of it, it will go to 0. Right? Same thing with that c in the first one. When I took the first derivative, c is a number, so when I took the derivative, it went to 0.
Even though it's the BX?
Well, this bx went to a b in the first derivative.
Oh, I was still looking at the first derivative, sorry.
Yeah, you're fine. All right. So let's plug these all in. Let's see what we get. Well, we have y double prime plus 4y prime minus 2y. And we want that to equal 2x squared minus 3x plus 6. That's what we want it to equal. Okay. So we're going to do a little bit of algebra. We are going to do this one in terms of a system of equations. Like, I'd like to show you how that works because we're going to be doing partial fractions in a few weeks and we're going to use systems of equations. So I'd like to just kind of walk through that process a few more times. Okay. So if I clean this up a little bit, I get 2a plus 8ax plus 4b minus 2ax squared minus 2bx minus 2c equals 2x squared minus 3x plus 6. Now I'll do this like very middle school where we're gonna collect all the like terms, okay? So I noticed that this negative 2ax squared is the only term on the left-hand side that has an x squared. And the only one on the right-hand side that has the x squared is the 2x squared. We can use that to say that negative 2a is equal to 2. All right. Now, it won't always be this straightforward, but we can see already that a is going to equal negative 1. Right? But let's go through and sort of create other equations. So for example, which terms only have a linear term? Well, 8ax minus 2bx is going to equal negative 3x, or 8a minus 2b equals negative 3. Now, because I already found a, I can go ahead and plug that in and find a value for b. So negative 8 minus 2b equals negative 3. Let's see, I get negative 5 equals 2b, and I get b equals negative 5 halves. And then last, we're going to create an equation that only has constants. 2a plus 4b minus 2c equals 6. And luckily for us, we already have our A and B values, so we can just plug those in. We get 2, let's see, minus 10 minus 2c equals 6. So negative, oh, no, negative 2. So negative 12 minus 6 is negative 18 equals 2c. So we get c equals negative 9. All right. Now you can also take this equation, create a matrix with these coefficients. That would also be okay. All right. And if you're going to use the matrix, just show me your matrix, like write out your matrix and then use your technology to find the actual answers. Okay. But all of this is to say that our particular solution has an A value of -1, B as -5/2, and C as -9. So we can say that y sub p equals -x² minus 5/2 x minus 9. All right, so we've got our y sub c in the pink, our y sub p in the orange, and we want to make sure we write that final solution. We're going to take y sub c and we're going to add y sub p. All right, I know it's a lot of writing. I try and model this because I'm doing all this writing too, right? So y equals y sub c plus y sub p. And so we end up with c1e to the -2 plus √6x plus c2e to the -2 minus √6x. That's my complementary part. And then minus x² minus 5/2 x minus 9. And this is the y sub p part. Okay. And once you've got all of that lined up, then you can go ahead and put a box or a circle around that to designate that that is indeed your final answer. Okay. So let me pause here for a moment before we move on. Any questions that are coming up for folks here? All right. So the last two questions here, all right, example 7, example 8 and example 9. In those two questions, we're only going to be looking for y sub p. Okay, so we'll get a chance to practice just that second part a little bit more. Okay. If you were still struggling a little bit with finding your y sub c, like C as in cat, I would go back to the 4.3 notes and maybe just like make a little table for yourself so you know what those different solutions are, okay? Because when we get to 4.7 this week, we're gonna be changing those a little bit for new cases. So we really wanna make sure those first 3 cases are actually pretty solid for us. All right. Let's go ahead and finish off these last 2 examples here. Now I can tell from the language in the question where it says find the particular solution, whoops, wrong color, that I'm only looking for my y sub p. All right, so there's only one step. I'm really just thinking about how do I match what I have to the table that I saw on the previous page. All right, and so this time we have 2 sine 3x. And so a good guess for y sub p might be A cosine of 3x plus B sine of 3x, right? If you prefer to use like a sub 1 and a sub 2 instead of a and b, that's also okay. All right, everybody sort of has a personal preference. I would just try it out, but you just want to make sure that you do not use the same letter in more than one place. Okay. So let's find our first derivative. Let's find our second derivative. Let's see. Negative 3a sine 3x plus 3b cosine 3x. And for the y double prime, we should end up with negative 9a cosine of 3x minus 9b sine of 3x. Okay, so I find those three. What am I going to do with them? I'm going to plug those into the left-hand side, that associated homogeneous differential equation side. And I'm going to see what values of a and b satisfy this differential equation. Okay. So we have y double prime minus y prime plus y and that should equal 2 sine 3x. Okay, 2 sine 3x. All right, now you'll notice that I put brackets around that middle term because you know what? I always mess up signs. I always forget to distribute them. I always forget to combine them. So I just put the brackets there anytime I see a subtraction to keep myself more accountable for this. But let's see what we get. All right. So we get negative 9a cosine 3x minus 9b sine of 3x plus 3a sine 3x minus 3b cosine 3x plus a cosine 3x plus b sine 3x equals 2 sine 3x. Whew, that's a lot. It turns out the way that we're going to create our system of equations to find a and b is we're going to cluster them by the sines and cosines. So for example, 9a cosine 3x, negative 3b cosine 3x, and a cosine 3x, those I can combine, right? And they're actually on the other side going to equal 0 because there are no cosine 3x's on the other side. Similarly, I can clump all the sine ones together. This term, 3a sine 3x, b sine 3x, together with the 2 sine 3x on the other side, I can create a second equation. Okay. So let's see what we get. We get negative 9a minus 3b plus a equals 0. So this is all of the yellow terms. And then separately, I have negative 9b plus 3a plus b equals 2. And that is all of the orange terms. I can clean this up a little bit before I make a matrix, and I would encourage you to do that. You should get negative 8a minus 3b equals 0. And your second one will be 3a minus 8b equals 2. Okay. So you can do a system of equations, you can put them into a matrix, whatever you do, please show me your work to get there. Okay, whatever method you choose, please show that work. In this case, we should end up with some fractions. So you want to make sure you turn it back into fractions. I would not leave it as a decimal, because you can already tell like something divided by 73 is perhaps not going to be a decimal that ends fairly quickly. And so we want to make sure we get all of the values so that our actual answer would be exact. All right. All we need to do at this point, we found our A and B. We're going to go back up here, Y sub P. Everywhere we see an A, we'll plug in the number we got for A. Everywhere we see a B, we'll plug in the number for B. And so our particular solution will be 6/73 cosine of 3x minus 16/73 sine of 3x. So there is example 8 all on one page for you. And while you're just finishing up writing that, I did want to say that I know I skip over some of this algebra stuff here. And if you're sitting here being like, she keeps talking about these matrices, but I forget how to do those, that's a valid question to ask me. So if you want to, ask on Discord or ask on Canvas about how you put these into a matrix, I would be happy to show you how to do that. Or if you're like, I don't really know how to do elimination or substitution, you can also ask me that. All right. So I'm not skipping it over because I think that, oh, it's like too dumb of a question to ask. I'm skipping over it because I think most of us right now are feeling pretty good about that. But if I'm way off base, please contact me and let me know so that I can help you figure that part out. Okay. All right, how are we feeling about these questions, like finding the particular solution piece? We feeling okay, not so okay? Yeah, and I think, Robert, you bring up a really great point, is that I don't think that any of you were these students, but if you think back to like when you learned how to factor, and if you learned it really well, it paid off, right? Maybe it took a while before you started to see the factoring again, but then it was like inside of another problem, a bigger problem that you had to use factoring with. And so if you got the factoring, then it made the other problems easier. And I think what we're seeing is a very condensed version of that, meaning like, if you're okay with the complementary solution, now that's only part of the puzzle because now we have a particular solution as well. Okay, and so that's sort of this week and the last week really come together as like, if last week didn't go well, then this week is going to be kind of hard. But that also means you can go back and fix last week to make the rest of this feel a little bit more comfortable. Okay. My one word of advice as you sort of study these topics would be to keep in mind, how do I know what steps I'm supposed to take? All right. And so whether it be a particular solution or a complementary solution or a general solution, like thinking what that might look like and when you go to which resource is probably the biggest thing that you can take away from this course. Okay. All right, I think we have just enough time to set up the last example. I don't know that we'll have time to finish it, but let's go ahead and see if we can go ahead and set up the particular solution for example 9. Okay. And so once again, we see the phrase particular solution. And so our focus is like, what's happening on this side? And how do we guess a solution form? Okay. So we sort of did one like this earlier where we had e to some power, but then times a linear function. And so a good guess for this one might be something like e to the 4x times the linear piece, ax plus b. Okay. You can distribute these if you want, because we're going to be taking a derivative. So you'll use product rule either way. It's really up to you whether this is easier for your brain to take a derivative of, or if this is easier for your brain to take a derivative of. Okay, so I'll leave that up to your personal preference. If you're fine using product rule here, great. If not, distribute and then know you'll use product here and just chain over here. I'll go ahead and use this first one here, no particular reason. But I get the derivative of e to the 4x is 4e to the 4x times ax plus b plus e to the 4x times the derivative of ax plus b, which is just a. Now, knowing that I need to take a second derivative, again, I can leave it like this, and I'll use product rule here, or if it makes me feel better, I can distribute, and then I'll have something, another version to take a derivative of. Okay, so I'll leave that up to you. I'm going to go ahead and use that product rule one more time. So I'll get 16e to the 4x times ax plus b plus 4e to the 4x times a plus 4a e to the 4x. Okay. We're going to take our y prime, our y double prime. We're going to substitute those into the left-hand side. And we're going to find the values of a and b that make it equal to x e to the 4x. So we get 16ax e to the 4x plus 16b e to the 4x plus 4a e to the 4x plus 4a e to the 4x. That's my y double prime minus 4 times my y prime and then finally minus 12. Ooh, didn't leave myself enough room. Minus 12 times my y guess. Still didn't leave myself enough room. Shrink that down. Make sure that's a 12, not a 1 squared. And we want this to equal x e to the 4x. Okay. Now I don't want to rush the computations here. So you can use this as an extra practice if you want to, but I'll let you know that your a should be negative 112 and your b should be negative 136. All right, so if you're like, oh, my computations are never that great, this could be a good exercise to just practice through and see what you are matching it to. And then at the very end, you would just go back to your y sub p, you plug in your number for A, your number for B, and you're good to go. Okay. All right, so folks, we're going to stop this video right here.